Video, we're going to be talking about graphs of functions and really all of the special characteristics that we could possibly talk about when we look at a graph. First of all, we're going to start with establishing interval notation, making sure that we can use that because we're going to describe a lot of things using that interval notation throughout these notes. So interval notation has two symbols. You can either use a bracket, which is going to mean that you have a closed or included point. So if you see a solid dot on a graph, that's closed or included. If you're including that value or talking about it, use a bracket. Or we could be using parentheses, and parentheses are for those open or not included points on your graph. Usually you see an open circle on a graph, that's an open point or a point that's not included in your domain. So I like to think about it as brackets that are hugging or gripping onto a value. That means it's included, whereas the parenthesis has more of a softer touch. It's not quite grabbing onto it, so it's not including that number. For example, let's do a little bit of practice where we just go back and forth between using an inequality or using interval notation. In this first one, we're talking about x values that are greater than -2. So all numbers that are greater than -2. But notice that it doesn't say also including -2. You don't have that greater than or equal to symbol. It's just greater than. So to symbolize that in interval notation, we would say -2. That's where we're starting, and then we're going greater than that. So we're going to use a parenthesis because we're not including -2. Values that are greater than -2 would go up to positive infinity and beyond. And we can never capture infinity or include it, so we always use a parenthesis when talking or using about infinity. And also, good point to bring up, when we use interval notation, we're always working negative to positive, either left to right on the x-axis or bottom to top on the y-axis. So always working negative to positive. All right, next, if we're given the interval notation, can we go backwards and think about what it may have looked like in inequality notation? So this is saying values that go from -5 up to infinity. And we're including -5, it's got that bracket. So values that are greater than -5 or equal to -5. We would write that using this inequality saying we have values that are greater than or equal to -5. Lastly, talk about some in-between values. This is what we do a lot using interval notation. Over here in the inequality, we're talking about values that are in between -10 and 35, but including -10, not including 35. So we're going to say -10 and use a bracket because we're including it, over to 35, but we're not including 35, so we'll put a parenthesis on it. All right, we use interval notation a lot to describe domain and range, among some other things we'll see later on. So let's practice using interval notation when we state domain and range of graphs or just function equations. Given a graph, the easiest thing to do is to identify what x values are being used. That's domain. So I like to draw little lines going from the left part of my function, the leftmost part of my function, over to the rightmost part of my function, and then just circle those values on the x-axis. So we're going from -5 over to -2, working left to right, and we don't include either of those values because we see open or not included points there on the ends. The range is talking about the outputs, or y values, that are given when we use this domain or those inputs. So again, I like to trace the top of my graph over to the y-axis and the bottom of my graph over to the y-axis. And then I know I'm talking about values that are in between those 2 points on my y-axis. So we're going from -4 up to +4. And again, we're not including either of those values, so we're going to use parentheses for both values. Let's take a look over here when we just see a function equation. Now, the easiest thing to do is to look at the graph. But I also want to show you how we could do it algebraically. So if you use your graphing calculator to look at the square root of x minus 4, you can see that it does have a restriction to its domain. We're not able to use all inputs. So let's see algebraically why that's true. Because a square root cannot be used to evaluate a negative number, we know that this value inside the square root needs to be greater than or equal to 0. We can't have a negative value occurring under the square root unless we talk about imaginary numbers, but we're not doing that. So we could set up an inequality saying that I know that the inside of that square root has to be greater than or equal to 0. So we'll say x minus 4 has to be greater than or equal to 0, and we can solve that inequality algebraically by just adding 4 to both sides. And now we know our domain has to be values that are greater than or equal to 4. So writing that in our interval notation, it could equal 4. So we'll use a bracket. And then it has to go towards positive infinity values. So parenthesis with infinity there. If you're looking at the graph, you also notice that the outputs start at 0 because if we were to plug a 4 in, the output would be 0. And remember, we can't go any lower than that or more negative than that. So our first output is going to be 0. We can include it. And then it goes higher. I mean, it goes really slow, but it does go higher towards infinity. So there's our range. So again, anytime you're looking at a function equation and you have a graphing utility available, the best thing to do is to look at the graph first and then go back to your algebra steps here and decide, like, why is the graph looking the way it is? Why are things restricted? And hopefully you can make sense of it. There's domain and range using interval notation. Here's another thing we can describe using interval notation. We can describe where on a graph we see it increasing or decreasing. And the way that we describe those intervals is by basically stating the domain at which you see that behavior happening. So anytime we state domain using our interval notation to describe increasing and decreasing values, this is what we're going to do. I like to label my slopes just with a positive, a negative, or a 0. It will help you as you advance in math. Getting into calculus, you'll be doing similar things. If a function is going up, it has a positive slope. If a function is going down, it has a negative slope. And somewhere in between, there should have been a 0 slope. And 0 slopes happen at peaks or valleys. We'll actually talk about that down here when we talk about minimum and maximum values. So I do want to talk about that first because I think what we can do with our graphing calculator here is going to help us in determining where we stop increasing or stop decreasing. So before I talk more about the intervals up there, let's go down here and use our calculator to do something pretty fancy. Another thing on a graph could be minimum and maximum values. So again, those are the peaks and the bottom of the valleys in your graphs. So we'll be able to visualize this here. We're going to graph this function, equation, and then we're going to look to see if it has a minimum or a maximum value. So let me get my calculator here. Use Desmos. I've graphed x cubed plus 3x squared minus 1. Sorry, not the right one. We want this one instead. Play with my graph here, sorry. All right. 3x squared minus 4x minus 2, right? Yeah, now we're good. Okay, here's our graph. We've got a quadratic here. It's opening up, or it's happy, and we have a minimum value occurring. We have this valley right here. For some functions, a relative minimum and an absolute minimum are the exact same thing. For quadratics, that's true. For other graphs, we'll talk about why some things are called relative maxes or mins, and some are absolute maxes or mins. So this one's got one and the same. It's got a relative minimum that's actually the absolute minimum. So on Desmos, you can actually just click there and then just hover over it to see the value. But on your graphing calculator, you actually have a function that gives you your minimum or maximum values. Just pressing a few buttons. So on your graphing calculator, there's usually a calc feature, and it's usually above the trace button. So you have to use shift or second to get to it. But once you open it up, it usually gives you some options to find minimums and maximums. So if you click on the minimum after you've plotted this graph, then you're able to go through a 3-step process and it will tell you the relative minimum. I can't go through that process on this video, it's just too confusing. So if you need help using your graphing calculator, please make sure and ask me in class how to get to this feature. But in the meantime, you can always look at Desmos here. So we said it was 0.667 and the output was negative 3.3. Let's check one more time. There it is. All right, let's look at one more, I think. We're going to graph negative x cubed plus x. So we can see that graph now. Notice that it has a relative minimum and a relative maximum. But notice that the graph is climbing higher and higher and higher. So the absolute maximum, I don't think it would ever get to one, but if it stopped somewhere up here, that absolute maximum would be greater than the relative max. So the relative is just because it's relative to this position on the graph. Same thing with the minimums. This is a relative minimum relative to this space on the graph, but know that there are lower values or more negative values that could be absolute minimums. All right, so we're asked to find the max and the min. You can use the feature on your graphing calculator or use Desmos here. Just hover over where that relative max is. We got 0.577 and the output is 0.385. So that should be our maximum right there. And the relative minimum, hover over that one, and we see that it's basically the same or exactly the same, but the opposite. That doesn't always happen. That just happens to be a coincidence for this graph. So again, looking at the bottom valleys or the top peaks to find your maxes and your mins. All right, going back up here, I think that's going to help us establish our intervals a little better here. For this graph, for this graph right here, we already established that we have an increasing interval starting at -3 on the x-axis and going to 0 on the x-axis. That's where our peak comes. So because we can't include the actual point, we're going to use open intervals here and describe that as -3 to 0. Then decreasing, you see that the graph is falling from 0 over to 2 on the x-axis. Not including 2, we got an open circle there. So we're going to use, again, open intervals right here. You may be asking, like, well, this is a closed point. How come we didn't put a bracket there? Or why didn't we put a bracket here at 0? The graph is still continuing. That value is on the graph. Well, it's because when you're talking about increasing and decreasing intervals, we don't really know what's about to happen right here. I mean, it's decreasing, but that could also change if the graph were to continue and do something different right there. Change direction. So we know that it's decreasing all the way up to that point, but not necessarily including that point. And the same thing here at 0, it's increasing and then it decreases. Well, at some point in between, it had to hit 0. And in fact, it has a 0 slope right here if x is 0. And so it's not increasing right there, it's 0. So the graph is increasing all the way until it gets to that point. So again, that's why we're using open intervals here. All right, one more time, we're going to use our graphing calculator to look at the behavior of this function. So plug that into your calculator, take a look at the graph, or use Desmos here. Let's see. What it looks like. That was that first one that I mistakenly tried to show you. All right, here we go. X cubed plus 3x squared minus 1. Yeah. We have 2 intervals where we're increasing. Notice that we're increasing here and we're increasing over here. And we have 1 interval where we're decreasing. So you can use that function that we just talked about using on our calculator where we find the max and min values, because that is where your behavior of your graph is going to change from increasing to decreasing. And so it's important to know where that peak is. So you can use that function on your calculator, or you can use it in Desmos here and just hover over the point. So we know we're increasing until we get to an x value of -2. And then we'll be increasing starting at 0 and increasing towards infinity. So the way that we write that, increasing from -infinity to -2, open interval, and then increasing from 0 to infinity. And the way that we just join those two sets is we use that union symbol. Some people put a comma, but since we're in advanced math, we might as well get used to using that symbol. Let's take a look at the decreasing interval. I said that it started to decrease right after -2 and stops decreasing right here, right before it gets to 0. So from -2 to 0 will be our decreasing interval. There is a way that eventually you'll be doing this in calculus. So this is an important concept that you will continue to be doing in the future. The way that we do it is that we take the derivative of the function, which gives us a slope equation. And if we know the slope is 0, well, the slope is 0 when we hit those relative maxes or mins, potentially. So if we know exactly where it hits the zeros, then we can test inputs on either side of that to determine whether our slope was negative or positive. And then we know what intervals we're increasing or decreasing. So we can see that we had that -2x value and that 0x value. That is where the graph was potentially changing directions. And that's what this little calculus step tells you. So until then, we got to use our calculator and just use those features on the calculator, or just look at the graph. All right, a couple more things, kind of random here. We want to be able to sketch a piecewise function. A piecewise function is just pieces of individual functions put together on one graph, and they may start or stop depending on what they're described in using this little domain notation right here. So we have a linear function, 2x plus 3, as long as our x values are less than or equal to 1. So what I tend to do is I graph it like I normally would, starting at the y-intercept with a positive slope of 2 over 1. And I draw it really lightly, and I take up as much of the graph as I can. And then I go back and I say, okay, where does the graph exist? And it only exists for x values that are less than or equal to 1. So then I would erase whatever I drew that was greater than 1. So that leaves behind this part of that linear equation. We got one more equation as part of this piecewise function. It's another linear equation with a y-intercept of 4 and a -1 slope. So we're going down 1, right 1. But it only starts with x values that are greater than 1. So I would draw it really lightly right here until I got to where I should be starting, and now I darken it up and make it solid. And so we can see the jump here. We were on this graph or this equation for all x values that were less than or greater than 1, and then when we got to right after 1, then we jumped to this graph. So 1 is included in the domain of this equation, but not included in the domain of this equation. Similarly, right over here, two more linear functions, just a different spot where they change. They're going to be changing at -4. So I plot my y-intercept at -6, and I do a slope down 1, right 2, down 1, right 2, and I would draw that all the way across, and then look at my domain. I'm only going to draw that graph if I have x values that are less than or equal to -4, so then I would erase anything that was greater than that, leaving behind this piece. Same thing here, we got a y-intercept of 5 and a slope of +1, so we could draw that whole graph right there. but then erase anything over here because the domain doesn't exist for values that are less than -4, only for values that are greater than -4. So we're on this graph until we hit -4, then as soon as we jump forward from there, we jump onto that graph. So sketching piecewise functions are just sketching individual functions and then paying attention to where they exist by the domain statements. All right, lastly, we're going to talk about what even and odd functions are. In your vocab, you can see a definition of it, but essentially even functions have a symmetry across the y-axis when they're graphed. Odd functions will have a symmetry across the origin, which is kind of a weird sort of symmetry. But you have an example in your vocab of what that looks like. One little trick with odd functions, trying to see that symmetry at the origin, if you actually take your graph or your pencil and put it on your graph at the origin and spin it, one half of your graph will spin to line up with the other half of the graph. So ask me in class if you want to see a visual of that. All right, but there is a way that we can actually just look at the function equation and determine whether it's even or odd. We don't have to look at the graph or the symmetry. As it turns out, functions that have variables that are all even numbers turn out to have that y-axis symmetry, and we call those even functions. Functions where the variables are all odd exponents, those end up having that symmetry about the origin, and we call those odd functions. If a function has a mix of even and odd exponents, well, then it doesn't have either of those symmetries, and we don't call it even or odd. We just say it's neither of those. So that's really the trick behind it. But I would encourage you to graph some of these or graph ones that would follow those rules and really investigate that symmetry and play around with their exponents to see if those rules hold up. All right, so a lot in that video. Hopefully you can practice it. Let me know if you got any questions in class.